Now, in this lecture, we find out the area of the small circle. In the drawing, we have a semicircle. This is a semicircle. Inside this semicircle, we have this circle. In addition, we know that line segment AQ equals to 2 units in its length. Line segment TB equals to 8 units in its length. This is angle PQ8, that is a right angle. This is angle STB, that is also a right angle. Again, our mission is to find out the area of this small circle. So first of all, we know that AB is the diameter of this semicircle. So AB is the diameter, it is absolutely a straight line. So if you focus on the upper side of the straight line AB at point Q, here the sum of the areas must be equal to 180 degrees according to rule 3 that states that the sum of the areas on one side of the straight line is equal to 180 degrees. In our drawing, it means that the rule means that the sum of the angles on the upper side of AB at point Q must be equal to 180 degrees. So which angles we have at the upper side of AB at point Q? We have this angle that is the right angle plus this missing angle. In total, they must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. Likewise, we focus on the upper side of AB at point T. Here, the sum of the angles must be also equal to 180 degrees according to rule 3. So which angles we have at the upper side of AB at point T? We have this angle that is the right angle plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we'll define the relevant points to this question with letters. We'll define the center of this big semicircle. This point is point H. We will define the center of this small circle. This point is point K. We will define the point of tendency of tangent ST with this small circle. This point is point L. We will define the point of tendency of tangent PQ with this small circle. This point is point J. And finally, we define the point of tendency of tangent AB with this small circle. This point is point M. In the next step, we will join points K and M together by straight line. What is the definition of line segment KM? Line segment KM starts from point K, that is the center of this small circle, and ends at point M, that is the point on the small circle itself. So this is exactly the definition of a radius. Therefore, KM is the radius of this small circle. We will define the radius of this small circle as x. Therefore, KM equals to x. Here we can implement rule 1. Repeat quickly on rule 1. According to rule 1, a tangent to the circle is perpendicular to the radius drawn to its point of tendency. So in the drawing we have a circle, and we also have tangent AB that is tangent to this circle at this point, point M. And we have the radius OM that is equal to R. The radius OM is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever your radius is drawn to the point of tendency, then tangent AB will be perpendicular to radius MQ. If AB is perpendicular to MQ, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees. According to this rule, rule 1. We can actually implement rule 1 in our drawing. Why? Because in our drawing we have the radius km is equal to x, the radius km is drawn to point M, that is the point of tendency of tangent AB with this small circle. And whenever we have radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MK. If AB is perpendicular to MK, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Okay. Likewise, we join points K and L together by a straight line. Line segment KL is the radius of this circle is equal to x. Again, we have the radius KL that is drawn to point L, therefore according to rule 1. This angle equals to 90 degrees, and this angle also equals to 90 degrees. By doing this construction, we actually created here quadrilateral KLTM. Besides quadrilateral KLTM, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this missing angle, in total it must be equal to 360 degrees. According to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. So inside the small quadrilateral KLTM, we have 4 right angles. And according to rule 6, any quadrilateral that has 4 right angles must be this rectangle if not a square. So we write to this small quadrilateral KLTM is a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle KLTM, side KL must be equal to the opposite side TM. But KL is x, therefore TM must be also equal to x. Likewise, according to the sum rule, in the same rectangle KLTM, side KM must be equal to the opposite side TL. But Km is x, therefore TL must be also equal to x. So actually we found out that quadrilateral KLTM is not a rectangle but a square because of the fact that all 3 sides are equal to each other. Inside of this square equals to x. So write it down. Quadrilateral KLTM is a square. Likewise, we join points K and J together by straight line. So again, we join points K and J together by straight line. Kj is of course the radius of this circle is equal to x. The radius Kj is drawn to point J. Therefore, according to this is the point of tendency of tangent PQ with this circle. Therefore, according to rule 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. So by doing this construction, you can deduce quadrilateral KJQM. Inside quadrilateral KJQM, we have 1, 2, 3 right angles. So therefore, this fourth angle must be equal to 90 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, inside quadrilateral KJQM, we have 4 right angles. And according to rule 6, you can relate to this quadrilateral as a rectangle. But we also know that the opposite sides of rectangle are equal to each other. So in rectangle KJQM, side KJ must be equal to the opposite side QM. But KJ is x, therefore QM must be also equal to x. Likewise, according to the sum rule, in the same rectangle KJQM, side KM must be equal to the opposite side JQ. But KM is x, therefore JQ must be also equal to x. So actually found out the quadrilateral KJQM is not a rectangle but a square because of the fact that all of its sides are equal to each other. Each side equals to x. So write it down. Angle JKL, this is angle JKL, is equal to 90 degrees plus 90 degrees, it is 180 degrees. So angle JKL equals to 180 degrees in size, and we know that any angle that is equal to 180 degrees in size must be a straight line. Therefore, JKL is a straight line. If JKL is a straight line, it means that JL is also a straight line. So JL is a straight line that touches the circle at 2 points, J and L. And we know that any straight line that touches the circle at 2 points, it is defined as a chord. Therefore, JL is a chord that passes for point K, that is the center of the circle, and we know that any chord that passes for the center of the circle must be the diameter of the circle. So I write it down. We actually found out that JL is the diameter of the circle. JL is the diameter of the circle. Anyway, JL as a diameter, it is absolutely a straight line. Because of the fact that JL is a straight line, it means that the shape JLTQ is a quadrilateral. Why? Because it has exactly 4 sides. 1, 2, 3, 4. Inside quadrilateral JLTQ, we have 4 right angles. 1, 2, 3, 4. And according to rule 6, any quadrilateral that has 4 right angles must be this rectangle if not a square. So we relate to quadrilateral JLTQ as a rectangle, but we know that the opposite sides of a rectangle are equal to each other. So in rectangle JLTQ, side JL must be equal to the opposite side QT. But JL is 2x, therefore QT must be also equal to 2x. So here, we shall find out that the length of QT is 2x. 2x, it is also the diameter of the circle, because the radius is x. So QT equals to 2x units in Snell. What is the radius of the big semicircle? We will define the radius of the big semicircle as capital R. Capital R is the radius of the big semicircle. But what is the value of capital R? What is exactly the value of the radius of the semicircle? The radius of this semicircle capital R will be equal to the diameter AB over 2. Again, the radius of this big semicircle capital R will be equal to AB, that is the diameter over 2. So capital R equals to AB over 2. But what is the length of the diameter AB? From the drawing, it is very easy to see that AB in total equals to 2 plus 8. 2 plus 8 is 10 plus 2x. Again, 2 plus 8 plus 2x is the value of AB, that is the diameter of the semicircle. 2 plus 8 is 10, and 10 plus 2x is the length of the diameter AB. So the length of AB equals to 10 plus 2x, and if we divide the diameter AB by 2, we get the radius R. So it is the radius R equals to the diameter AB, that is 10 plus 2x over 2. So the radius R equals to 10 over 2, that is 5, plus 2x over 2 is x. So in total, we actually found out that the radius capital R of the big semicircle equals to x plus 5 units in its length. Okay. What is the length of this line segment MH? From the drawing, it is very easy to see that M edge or edge M in total equals to A edge, that is the radius of the big semicircle, minus AQ minus QM. Again, A edge minus AQ minus QM equals to edge M or M edge. Okay, so I write it down. If I found out that the length of this slice segment M edge equals to A edge, that is the radius of the semicircle, minus AQ, that is 2, minus QM, that is X. Repeat again. I actually found out that the length of line segment M edge equals to A edge, that is the radius of the big semicircle, minus AQ, that is 2, minus QM, that is X. So in total, M edge equals to A edge, that is the radius of the semicircle. We have already found out that the radius of the semicircle, capital R, equals to X plus 5, minus AQ. AQ is 2, minus QM. QM is X. So in total, M edge equals to X minus X is 0, 5 minus 2 is 3. So in total, M edge equals to 3 units in its length. So M edge equals to 3 units in its length. Here we can actually implement all 9. Why? Because we have an internal notch between the big semicircle and this small circle. That is to say, they are touching each other internally at this point, and whenever we have an internal notch between two circles, you can implement all 9. I'll repeat quickly on all 9. According to all 9, if two circles touch each other internally, then the side line connects their centers together, passes through their touching point. Those two circles touch each other internally at this point, point P. The center of the big circle is 0 at point O. The center of this small circle is 0 at point M. The side line that connects their centers together is of course the side line OM, and this side line OM must pass through point P, that is their touching point. Again, the side line OM must pass through their touching point, that is actually point P. Or OMP is one side line. Again, OMP is one side line according to this rule, all 9. So we can actually implement all 9 in our drawing. Why? Because in our drawing we have an internal notch between the small circle and the big semicircle. This is to say, they are touching each other internally at this point. Therefore, we can implement here all 9. The center of the big semicircle is here at point H. The center of this small circle is here at point K. And the side line that connects the centers together is the side line HK. And the side line HK must pass through their touching point. That is this point. So I connect the centers H and K together, and the side line HK must pass through this point, that is their touching point, according to all 9. You can definitely see that the side line HK passes through their touching point, this point. Again, the side line HK passes through their touching point, that is this point. We define the touching point of the small circle with the big semicircle. This point is point D. You can definitely see from the drawing that the side line HK that connects the centers together passes through point D, that is their touching point. Or HKD is one side line, and HKD is one side line. If HKD is one side line, it means that HD is also a side line. HD is a side line. But what is exactly the definition of the side line HD? The side line HD starts from point H, that is the center of the semicircle, and that's at point D, that is the point of the semicircle itself. So this is exactly the definition of a radius. Therefore, HD is the radius of this semicircle that is equal to x plus 5. So HD equals to x plus 5, it is the radius of the semicircle. What is the definition of line segment KD? Line segment KD starts from this point K, that is the center of this small circle, and then at point D, that is the point of the small circle itself. So for KD is the radius of this small circle, that is equal to x according to our definition. So KD equals to x. And what is the length of the missing side? Side KH. The missing side KH equals to DH minus DK. Again, DH minus DK equals to KH. So I write it now. The missing side KH equals to DH minus DK. Okay, again, if we found out that the missing side KH equals to DH minus DK. So KH equals to DH, or HD, it is the same. HD is the radius of the semicircle, that is x plus 5, minus DK. DK is the radius of the small circle, that is x. So in total, the missing side KH equals to x plus 5 minus x. X minus x is 0, so x will get cancelled, and we left only with 5. So we found out that the missing side KH equals to 5 units in its length. So I write it down. This is the missing side KH. This equals to 5 units in its length, so I write it down in the original line. This side equals to 5 units in its length. In the next step, I'll copy the right triangle KMH in a new page, and we represent the Pythagoras theorem with this right triangle KMH. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is a abbreviation for Pythagoras theorem. Side KM equals to x. For the green right triangle, MH equals to 3, and the hypotenuse KH equals to 5. So actually, this is the right green triangle KMH that I copied from the original domain. According to the Pythagoras theorem, in this right triangle KMH, KH square equals to KM square plus MH square. Again, KH square equals to KM square plus MH square. So write it down. KH square, that is the square of the hypotenuse of the right triangle KMH, equals to KM square plus MH square. The hypotenuse kh equals to 5, therefore kh squared is 5 squared, that is 25. And it is equals to km squared. Km is x, therefore km squared is x squared, plus mh squared. mh is 3, therefore mh squared is 3 squared, that is 9. So in total, actually found out that 25 equals to x squared plus 9. We subtract 9 from this equation. And finally we get that x squared equals to 25 constant is 16. So x squared equals to 16. We take out of this equation, and finally we get that x, that is the radius of the small circle, equals to the square root of 16, that is 4. So actually, I found out that the radius of this small circle, x equals to 4 units in its length. Our mission is to find out the area of this small circle. So the area of any circle equals to pi times the radius of the circle squared. And therefore the area of our circle will be equal to pi times the radius squared. The radius is x, therefore the radius squared is x squared. So the area of our circle equals to pi x squared. We just found out that x squared equals to 16, so we substitute x squared in this equation by 16. We get that the area of the circle, that the area that we are looking for, equals to pi, and x squared is 16. So we found out that the area of this small circle equals to either 16 pi square units, or in terms of numbers, it is equals to 50.265 square units. Repeat again, actually found out that the area of this small circle equals to either 16 pi square units, or in terms of numbers, it is equals to 50.265 square units. So in the next step, I will summarize the lecture. Our mission in this lecture is to find out the radius of this small circle. So in the drawing we have a semicircle. You know that 978Q equals to 2 units in its length, 970TB equals to 8 units in its length. This is angle PQA, this is a right angle. This is angle STB, this is also a right angle. Again, our mission is to find out the area of this small circle. So first of all, we know that AB is the diameter of this semicircle, big semicircle. AB is a diameter, it is absolutely a straight line. So if you focus on the upper side of the straight line AB at point Q, the sum of the angles must be equal to 180 degrees, according to rule 3. That states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of AB at point Q? We have this angle, that is a right angle, plus the missing angle. This missing angle, in total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. Likewise, we focus on the upper side of AB at point T. Here, the sum of the angles must be equal to 180 degrees according to rule 3. So, which angles we have at the upper side of AB at point T? We have this angle, that is the right angle, plus this missing angle. In total, they must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we defined the relevant points to this question with letters. We defined the center of this big semicircle, this point as point H. We defined the center of this circle, this point as point K. We define the point of tendency of tangent ST with this small circle, this point is point L. We define the point of tendency of tangent PQ with this small circle, this point is point J. Likewise, we define the point of tendency of tangent AB with this small circle, this point is point M. And finally, we defined the touching point of this small circle with the big semicircle, this point is point D. In the next step, we joined points K and M together by a straight line. What is the definition of right segment KM? Right segment KM starts from point K, that is the center of this small circle, and then at point M, that is the point on the small circle itself. So this is exactly the definition of a radius. Therefore, Km is the radius of this small circle. We define the radius of this small circle as x, therefore Km equals to x. Here we can implement rule 1. Because of the fact that the radius Km that is equal to x, the radius km is drawn to point M, that is the point of tendency of tangent AB with this small circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MQ. If AB is perpendicular to MQ, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we join points K and N together by side line. KL is the radius of this small circle, that is equal to x according to our definition. The radius KL is drawn to point M, that is the point of tendency of tangent ST with this small circle, and according to rule 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. So by doing this construction, creating quadrilateral KLTM, inside quadrilateral KLTM, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees, according to the rule that the sum of the angles on one side, the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. So inside quadrilateral KLTM, we have 4 right angles. And according to rule 6, any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So in relation to this quadrilateral that has 4 right angles, it's a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So a rectangle KLTM, side KL must be equal to the opposite side TM. But KL is x, therefore TM must be also equal to x. Likewise, according to the same rule, in the same rectangle KLTM, side KM must be equal to the opposite side LT. But Km is x, therefore LT must be also equal to x. So actually found out that quadrilateral KLTM is not a rectangle but a square because of the fact that all of its sides are equal to each other. Likewise, we join points K and S together, K and J together by side line. Kj is the radius of this small circle, that is equal to x. The radius Kj is drawn to point J, that is to point J, that is the point of tendency of tangent PQ with this small circle. Therefore, according to rule 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. So by doing this construction, you can deduct quadrilateral JKMQ. Inside quadrilateral JKMQ, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in size, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. So inside the quadrilateral JKMQ, we have 4 right angles. And therefore, according to rule 6, we can relate to this quadrilateral as a rectangle. So JKMQ is a rectangle, but we also know that the opposite sides of a rectangle are equal to each other. So a rectangle JKMQ, side JK must be equal to the opposite side MQ, but JK is x, therefore Q must be also equal to x. Likewise, according to the same rule, in the same rectangle JKMQ, side KM must be equal to the opposite side JQ, but KM is x, therefore JQ must be also equal to x. So actually found out that quadrilateral JKMQ is not a rectangle but a square because of the fact that all of its sides are equal to each other. And angle JKL, this is angle JKL, that is equals to 90 degrees plus 90 degrees, that is 180 degrees. And you know that any angle that is equals to 180 degrees in size must be a straight line. Therefore, JKL is a straight line. If JKL is a straight line, it means that JL is a straight line. JL is a straight line, and therefore the shape JL, the shape JL, edge, the shape JL, edge, the shape JLTQ, the shape JLTQ is a quadrilateral. Why? Because it has 4 sides. 1, 2, 3, 4. So inside quadrilateral JLTQ, we have 1, 2, 3, 4 right angles. And according to rule 6, any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we get to quadrilateral JLTQ is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle JLTQ, side JL must be equal to the opposite side TQ. But JL is 2x. It is the diameter of the small circle. Therefore, QM must be also equal to 2x. Okay. In the next step, we actually found out that Repeat again, YJL is the diameter of the semicircle. JL is a straight line that touches the circle because this angle equals to 180 degrees, therefore JL is a straight line that touches the circle 2 points J and L, therefore JL is a chord that passes through point K, that is the center of the circle, and we know that any chord that passes through the center of the circle must be the diameter of the circle. Therefore JL is the diameter of the circle. Repeat again, JL is the diameter of the circle. As already mentioned before, and quadrilateral JL, the shape JLTQ is a quadrilateral that has 4 right angles, and according to rule 6, any quadrilateral that has 4 right angles must be this rectangle if not a square. So in this quadrilateral JLTQ, we have 4 right angles, therefore we can relate to this quadrilateral as a rectangle, and we know that the opposite sides of a rectangle are equal to each other. So in rectangle JLTQ, side JL must be equal to the opposite side TQ, but JL is 2x, this is the diameter of the circle, therefore TQ must be also equal to 2x. In the next step, we found out the radius of this big semicircle. We define the radius of this semicircle as capital R. What is the value of capital R? That is the radius of the semicircle. The radius of the semicircle, capital R, must be equal to AB, that is the diameter of the semicircle, over 2. Repeat again. Again, capital R is the radius of the semicircle according to our definition. The capital R, that is the radius of the semicircle, equals to the diameter AB over 2. And diameter AB in total equals to 2 plus 8, that is 10, plus 2x. Again, the diameter AB in total equals to 10 plus 2x. The diameter AB is 10 plus 2x, and so, therefore the radius is the diameter over 2, AB over 2. It is AB is 10 plus 2x, so it is 10 plus 2x over 2. 10 plus 2x over 2 is 10 over 2, that is 5, plus 2x over 2, that is x. So in total, the radius R equals to 5 plus x. R equals to x plus 5 units in itself. So we found out that the radius of this big semicircle equals to x plus 5 units in its length. Okay, in the next step, we found out the length of this line segment M edge. What is the length of M edge? From the dominant, it's very easy to see that M edge in total equals to A edge, that is the radius of the semicircle, minus AQ minus QM. Again, A edge minus AQ minus QM equals to M edge. Repeat again, M edge, the missing side M edge equals to A edge, that is the radius of the semicircle, minus AQ, that is 2, minus QM, that is x. Again, M edge is A edge, that is the radius of the semicircle, and the radius of the semicircle equals to x plus 5, minus AQ, AQ is 2, minus QM, QM is x. So in total, M edge equals to x plus 5, minus 2, minus x. X minus x is 0, and 5 minus 2 is 3. So in total, we actually found out that the missing side M edge equals to 3 units in its length. Okay, so here we have an internal notch between the big semicircle and this small circle. That is to say, they are touching each other internally at point D. Point D is their touching point, and whenever we have an internal notch between two circles, you can implement rule 9. Okay, I'll take quickly of rule 9. According to rule 9, if two circles touch each other internally, then the straight line that connects their centers together passes through their touching point. Those two circles touch each other internally at point P. The center of the big circle is 0 at point O. The center of this small circle is 0 at point M. And the straight line that connects their centers together is the straight line OM. And according to this rule 9, the straight line OM must pass through point P, that is their touching point. Again, the straight line OM must pass for the attaching point, that is point P. Or OMP is one straight line. Again, OMP is one straight line. Okay, we can implement all 9 in our drawing because we have in our drawing an internal length between the big semicircle with this small semicircle at point D. That is to say, they are touching each other internally at point D. The center of the big semicircle is here at point H. The center of this small circle is here at point K. The straight line that connects the centers together is the straight line HK. And according to rule 9, the straight line HK must pass for point D, that is their touching point. Again, the straight line HK must pass for their touching point, that is point D. Or HKD is one straight line. HKD is one straight line according to rule 9. If HKD is one straight line, it means that HD is also a straight line. HD is a straight line. But what is exactly the definition of the straight line HD? The straight line HD starts from point H, that is the center of the semicircle, and then at point D, that is the point of the semicircle itself. So this is exactly the definition of a radius. Therefore, HD is the radius of this semicircle, that is equal to x plus 5 units in center. Again, HD is the radius of the semicircle, that is equal to x plus 5. HD equals to x plus 5. What is the definition of line segment DK or KD? Line segment KD starts from point K, that is the center of the small circle, and that's at point D, that is the point of the small circle itself. So this is exactly the definition of a radius. Therefore, KD is the radius of this small circle, that is equal to x. And again here, KD equals to x, and HD equals to x plus 5. Therefore, the missing side KH, equals to DH minus DK. Again, DH minus DK, DH minus DK equals to the missing side KH. Repeat again, the missing side KH equals to DH minus DK. So the missing side KH equals to DH, that is the radius of the semicircle, that is x plus 5, minus KD is x. So in total, the missing side KH equals to x plus 5 minus x. X minus x is 0, so we're left only with 5. So the missing side KH equals to 5. This is the missing side KH, that is equals to 5 units in itself. In the next step, I copied the right green triangle KMH in a new page, and we implemented the Pythagoras theorem of this right green triangle KMH. This is the right green triangle KMH that I copied from the original drawing. Side KM equals to x. It is the radius of the semicircle. It is the radius of the small circle. Side MH equals to 4 units in itself, and the hypotenuse KH equals to 5 units in itself. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. In this right triangle KMH, it means that KH square equals to KM square plus MH square. Again, KH square equals to KM square plus MH square. KH is 5, therefore KH square is 5 square, that is 25. And it is equals to Km square. Km is x, therefore Km square is x square plus MH square. MH is 3, therefore MH square is 3 square, that is 9. So in total, according to the Pythagoras theorem, I actually found out that 25 equals to x square plus 9. Here we subtracted 9 from this equation, and we found out that x squared equals to 25 minus 9, that is 16. We took out of this equation and found out that x, that is the radius of the small circle, equals to the square root of 16, that is 4. So the radius of this small circle, x, equals to 4 units in its length. Our mission is to find out the area of this small circle. The area of any circle equals to pi times the radius of the circle squared. And therefore, the area of our circle, the area of this small circle, must be equal to pi times the radius of this circle squared. The radius of this circle is x, therefore the radius squared is x squared. So the area of our circle equals to pi x squared. And we already found out that x squared equals to 16, therefore we can substitute x squared in this equation by 16. We did it and found out actually that the area of this small circle equals to either 16 pi square units In terms of numbers, the area of this circle equals to 50.265 square units. I repeat again, the area of this small circle that is inside the big semicircle equals to either 16 pi square units, or in terms of numbers, it is equals to 50.265 square units. Okay, thank you very much.